Alright guys, welcome to part 3 of our stoichiometry video. This final problem is going to have all the bells and whistles, and hopefully you'll see that the process is the same throughout. This one's just a little bit more work. So let's dive right into our first problem here. It reads, 3.5 liters of hydrogen chloride is bubbled into a solution containing 13.7 grams of magnesium hydroxide. How many water molecules form? So we have a lot to do here to begin with. First of all, we're going to have to write a balanced chemical equation, predict the products of it, and then begin our stoichiometric process. One point of note, you'll notice this is an odd way to say this molecule, hydrogen chloride. Well, typically we would call this hydrochloric acid. So why are we giving it this bizarre name? Well, because it's a gas. When we have a binary acid in a gaseous form, we name it like this, hydrogen chloride, hydrogen fluoride, and so on. So as soon as this is bubbled into the solution, meaning bubbled into water, we'll call it by its regular name, hydrochloric acid. This is only true of the binary acids, not true of the oxyacids that we had learned about previously. But without further ado, let's write our chemical equation. So hydrogen chloride, we know that hydrogen is +1, chlorine is -1. Even though this is a covalent compound, we can use our charge ratios here to write a formula of HCl. We're reacting this with a solution containing magnesium hydroxide. So that's the particle of interest here. Magnesium, if we look, is an alkaline earth metal. It's +2. Hydroxide is a polyatomic ion, -1. So our formula is as follows, MgOH2. This is a special kind of double replacement called a neutralization. Why a neutralization? Well, we have an acid, hydrochloric acid, reacting with a base, magnesium hydroxide. The products of a neutralization are always water molecule, H2O, which the problem gave us a clue of, and some kind of salt. In this case, it's going to be magnesium chloride. Recalling that magnesium is +2 and chlorine is -1, so MgCl2. Now all we need to do is balance this. We see there are 2 chlorine on the product side, 1 chlorine on the reactant side, so we're going to put a big coefficient of 2 in front. Now if we looked on the reactant side, we have a total of 4 hydrogen, but only 2 over here. So we're going to put a 2 here. This balances the hydrogen but makes 2 oxygen, but there are 2 oxygen here. So now we have our balanced chemical reaction. So where do we go from here? Well, there are a number of different ways to solve a stoichiometry problem. And the way I'm about to show you is actually a little different than what I would typically teach in class, but I think it's a little shorter and a little easier for you guys to be able to understand given the format we're working in. So as we mentioned before, the mole is the only thing that goes on the bottom or underground. Grams, particles, or liters go on top. So I'm going to pull those out of my problem. I have 3.5 liters of hydrogen chloride or hydrochloric acid. Liters of a gas, so we're dealing with a volume. Now we're going to just assume that this is at STP, or standard temperature and pressure, so we can work our problem out. And we have a solution containing 13.7 grams, a mass, of magnesium hydroxide. And it wants us to determine how many water molecules. So that's a particle amount. So we need to get to molecules of water. So step 1 in any of these is to turn both into moles. We don't know which one is the limiting reagent just by looking at this problem. The numbers are complex enough that we can't immediately see. But what we can do, just like the squares and triangles making diamonds, we can go through and see which one of these produces the least amount of product. Whichever one produces the least amount of product will be the limiting reagent, and therefore that amount of product produced by the limiting reagent will be the real amount made. Once we've turned both of these into moles, we're going to use the mole ratios to turn them into moles of water molecule. The ratio between hydrochloric acid and water molecule is 2 to 2, or simplified 1 to 1. The ratio between magnesium hydroxide and water molecule is 1 to 2. And then the final step will be turning these into molecules, in which case we'll use Avogadro's number. If you're wondering where I'm getting some of this stuff, refer back to the mole island video and you can see what pathways lead to all these grams, particles, liters, and so on. So I'm gonna follow my roadmap and do these as 2 individual problems, and then we'll analyze the numbers at the very end. The first one, we're gonna take 3.5 liters of hydrochloric acid. To turn this into moles, we know that to turn a liter or a volume amount of any gas at standard temperature and pressure occupies 22.4 liters of space if we have 1 mole. So we know that for every 22.4 liters, there's 1 mole of any gas. The liters cancel for us, and that leaves us with the unit mole of hydrochloric acid. Following our roadmap, that's where we want to be. The next step is to use the ratio. Now, again, in this case, the ratio won't change anything mathematically for us, but we're going to include it anyway, just for unit's sake. So the next step is to turn the mole of hydrochloric acid into mole of water molecule. So I know that for every 1 hydrochloric acid, we have 1 water molecule. That cancels the hydrochloric acid for us, and we're at mole of H2O. So now we're here. The last step in this portion of the problem is to turn the mole of water into molecules of water. So we're going to use Avogadro's number. And I know that if I have 1 mole of any substance, I have 6.02 times 10 to the power 23 particles of that substance. And my particle in this case is molecule. Now, I'm not going to bother computing this just yet. We'll do that here in a second. The second portion of the problem deals with the magnesium hydroxide, so we're going to do that right below for comparison's sake. So I'm going to take the 13.7 grams of magnesium hydroxide. I want to turn that into moles. When I'm dealing with mass or grams, to turn that into moles, I need the molar mass. So we're going to reference our periodic table. I see that in 1 particle of magnesium hydroxide, I have 1 magnesium, which is 24.3 grams per mole. There are 2 total oxygen here, so plus 16 times 2, plus the 2 hydrogen, so 2 times 1.01, and we get a molar mass of 58.32 grams per mole. So for every 1 mole of magnesium hydroxide, we have 58.32 grams. Now in this case, the ratio will make a mathematical difference for us. We see it's 1 to 2, so we know that for every 1 magnesium hydroxide consumed, 2 water molecules appear, so 2 H2O on top. That cancels the magnesium hydroxide. The grams had previously canceled, so we're at mole of water molecule. We're here. The final step is to use Avogadro's number again to turn this into molecules of water. For every 1 mole. Now what we can do is the computational portion. So I'm going to go back to the beginning. 3.5 divided by 22.4. 1 over 1 is 1, so we're not going to bother with that step in our calculator, times 6.02 times 10 to the power 23, and we get, rounding for significant figures, 9.4 times 10 to the power 22 molecules of water. For the bottom one, we have 13.7 grams divided by 58.32. Now in this step, it will matter. So we have 2 over 1, so times 2 times Avogadro's number. And we get 2.83 times 10 to the power 23 molecules water. Now, with particles, you have to be careful. The 9 is a bigger number than the 2, but look at the exponent. This is power 22. This is power 23. This number is substantially larger. This is the larger quantity. So, the amount of water molecule made is actually the 9.4 times 10 to the power 22, because that's the smaller amount. Don't let the big numbers in front fool you. So this is 9.4 times 10 to the power 22. This was 2.83 times 10 to the power 23. So that means this is the real amount of product made. This is our theoretical yield. That means the hydrochloric acid or hydrogen chloride is our limiting reagent. And our magnesium hydroxide was the excess reagent. And now we've solved the problem with all the bells and whistles. We went from liters to moles to molecules, grams to moles to molecules. We've done a limiting reagent problem. We've identified excess, limiting, and we found a theoretical yield. So I hope this helped you in this 3-part series. I'll be continuing to post more videos. There are a few more special tricks and things we can add along the way, but I really hope this helps you out a lot. Continue sending me your questions on Remind and enjoy your weekend. See you back here next time, guys.